In this video, we're going to learn about the hexagonal close packing crystal structure and how to find its coordination number. I already made a video about coordination numbers in the past, but that one only covered cubic lattices, so you can treat this one as an extension of that. In order to find the coordination number of any lattice, we need to recall its definition. The coordination number is the number of atoms that are the shortest possible distance from a given atom. So if you look at one particular atom inside of a lattice, the number of nearest neighbors it has is the coordination number of that lattice. We also need to keep in mind that atoms are treated as solid spheres in this model, and the shortest possible distance between two solid spheres is obviously touching distance. So asking how many nearest neighbors an atom has is pretty much the same thing as asking how many atoms it touches. So in order to find the coordination number, we need to check where and how atoms touch. Now, for the hexagonal close packing crystal structure, these three images are basically the same. Here we have the unit cell, here we have the model where the atoms are solid spheres, and here we have basically the same image as this one, but pulled apart so you can see each layer. These 7 atoms right here correspond to the upper hexagon, these 7 atoms correspond to the lower hexagon, and in addition to that, the hexagonal close packing unit cell has 3 central atoms sandwiched in between those. Those are the green ones. Now, in order to find the coordination number, we need to choose one atom as our observation point, so to speak. And for the sake of simplicity, we're going to choose the one in the center of one of the hexagonal faces. From this image right here, we learn that the central atom of the upper hexagonal face touches all of the other atoms in that face. So in its own layer, it has 6 nearest neighbors. In our unit cell, that corresponds to those 6 right here. But since we are in 3 dimensions, we need to take the layers above and below into consideration as well. Now, the hexagonal close packing structure has an AB-AB layering. That means if this is the A layer and this is the B layer, if we extend the structure upward or downward, it always extends in an alternating fashion. So here would be B, and here would be B as well. Now, in between those 2 A layers, we have those 3 atoms in the unit cell. And if you imagine placing 3 balls in an arrangement like this, so they form a triangle, there's a little gap in the middle. And that gap is exactly where the central atom of the A layer sits. So this central atom touches not only the 6 neighbors in its own layer, but also the 3 atoms in the layer below. And since the structure extends in all 3 dimensions, it also touches the 3 atoms from the B layer above. That corresponds to this one, and this one, and also to this one, and this one in the B layer above. Adding all of those up, we have 6 nearest neighbors in its own layer, 3 below, and 3 above, which makes 12 nearest neighbors in total. So the HCP structure has a coordination number of 12. One of the aspects that make the coordination number so special is that it is the same no matter what atom you choose as a starting point. And for the HCP structure, that becomes very clear if you look at it from above. If we suppose that A corresponds to the red balls in this image, and B corresponds to the green balls in this image, the atom we picked as our origin could, for example, have been this one. Here we can see that it has 6 nearest neighbors in its own layer, and it also touches the 3 Bs above and below. And we can also see, what I visualized here, that the A atom sits in the gap formed by those 3 Bs. So it's placed like this. Now, if we picked a B atom, for example this one, which corresponds to this in the unit cell, we can see that it too has 6 nearest neighbors in its own layer, and it also touches the 3 A's above and below. Both the A layer and the B layer expand sideways too, but since we're focusing on the unit cell here, and the unit cell has a hexagonal shape and hexagonal faces, if this is the central atom of one of the faces, the unit cell would look like this. which means we have those 3 Bs, but the Bs around it are not part of the unit cell anymore. And that's why we only have 3 atoms from the B layer inside of the unit cell, even though both the A layer and the B layer expand sideways too. I really hope you found this video helpful, and if you have any feedback or ideas or suggestions, please type them into the comments. Thank you so much for watching, and see you in the next one.